Good afternoon, class. Is this thing on? It is on? Oh, okay. Good afternoon, class. Today we're going to be looking at operations on functions, the difference, quotient, and composition of functions. When I say operations on functions, I'm talking about the four real number operations, addition, subtraction, multiplication, and division. They can be expanded to functions. So first thing we're looking at is addition, subtraction, multiplication, and division. And algebraically, there's really nothing new at this point in terms of addition, subtraction, multiplication, and division. It's just how the notation that we're using. Addition of functions is just standard algebraic addition. Subtraction of functions is algebraic subtraction. Likewise for multiplication and division. You'll see what I mean when we look at the first problem. So number one. Now y'all need to help me remember to be switching. Here's problem one. They give us two functions, f of x and g of x. They want us to find f plus g, f minus g. That third notation, fg, there's no operation between them, so if you don't see an operation, you assume what? Multiplication, and then f divided by g. Notice they want us to give the domain of each. While we're looking at this, before I write the problem, or while I'm writing the problem down, who can tell me what the domain of f and the domain of g are? Look at f of x. These were the easiest ones to find the domain of in the homework assignment the last time. I think there was one function like this that had no fractions, it had no radicals, no square roots. What did we say? All real numbers, unless you're told differently. You are to assume this is a polynomial. In particular, it's a binomial. You can plug any number you want to for x, any real number. You're going to get a real number, not an imaginary number, not a denominator of 0. So, well, they don't ask us for the domain of f and g, but it's still a good review. They want us to find f plus g, f minus g, f times g, and f divided by g. First of all, f plus g. F plus g in terms of x. This notation is what's new. And all that means is you take f of x and you add g of x to it. So f of x, that's a 3x plus 5. Plus, that plus I just wrote down is the plus that's right there. Now we want to add g of x, 2x minus 7. Addition of functions is just plain old algebraic addition. If we didn't have this first line there, if we had just come in and I'd written this down and said, let's perform this addition, you know, well, you got to combine like terms. 3x plus 2x, that gives you 5x. What's your constant term going to be? You have a positive 5 minus 7, which gives me, so 5x minus 2 is my answer for f plus g. I'm going to go ahead and find all four of these things, and then I'll type the answers in all at once, okay? Now, f minus g, you want f minus g in terms of x. That says take f of x, and you're going to subtract. That minus there is this minus I'm writing right there. You're going to subtract g of x. Now, when you have a minus, we know f of x is 3x plus 5. But we have that minus sitting in front of g of x. What are we going to have to do there when you have a minus sitting in front of several terms? Change the sign, you're distributing that negative. I agree. The f of x, that's 3x plus 5. We could enclose that in parentheses if we wanted to. G of x is 2x minus 7. That first set of parentheses is unnecessary. I didn't even need to write it down. I just thought it looked better writing of the parentheses because this second set is not unnecessary. You have two terms with a minus in front. You're going to have to go through and distribute to change the signs. So you get the first set, I'll just drop 3x plus 5. And then I'll have a minus 2x. What else will I have? A plus 7. I agree. All that's new is just this notation of naming the expressions. And what does it mean, f minus g? It's exactly what you think. Take f of x minus g of x. After that first line, there's no new algebra here. We know what to do. We knew we had to distribute the minus to get rid of the parentheses. You have a 3x minus 2x. That gives me a 1x. What else? 5 plus 7 gives me a plus 12 for my final answer for f minus g. Addition and subtraction of functions is just plain old algebraic addition and subtraction. Now, f times g. That means you're going to take the rule for f of x and multiply it by g of x. We've certainly done this stuff enough. You're going to take f of x, 3x plus 5, and you're going to multiply it by g of x is 2x minus 7. What are we going to have to do here? The algebra is not new. We've been multiplying things like this. All that's new is what does that FG notation mean? What are we going to have to do to perform this multiplication? FOIL it out. First, 3x times 2x gives me a 6x squared. Outer, 3x times a negative 7 gives me a minus 21x. Inner plus 10x, I agree. Last, okay, I agree. Once again, once we get down to performing the actual multiplication, there's nothing new. It's just that notation. That's what's new. And we can combine like terms. That'll give us a 6x squared. Negative 21x plus 10x gives us a minus 11x. We still have that minus 35. Well, everyone knows that division is the hardest, right? So let's see. Of the four operations, addition, subtraction, multiplication, and division, f divided by g. That means you're going to take f of x on top and put g of x on the bottom. F of x, they gave us, was 3x plus 5. G of x was 2x minus 7. And normally we'd try to factor and cancel. Do we have any common factors? Could these things even be factored? Nope. There it is. You're finished. So in this case, division was probably the easiest one of all. And before we get timed out, let me type those answers in. Then we'll worry about their domains. F plus g of x, that's a 5x minus 2. F minus g, that is x plus 12. F times g, that's a 6x squared. Get out of the exponent. Minus 11x minus 35. And finally, f divided by g. I'll use my fraction bar. On top we have a 3x plus 5. And on the bottom we have a 2x minus 7. And now they want the domains. This is one of those times where the little hot button, negative infinity to positive infinity, would be mighty nice, but we don't have that. Let's come back to my paper. We've already said that the domain of f is all real numbers. The domain of g is all real numbers. There are no fractions, no radicals. Look through your work. For f plus g, did you pick up any fractions or square roots as you went through that work? No fractions, no square roots, so the domain is all real numbers. You can't just look at the final answer for this, because suppose we had something like a square root of x that wound up being squared. Well, even though that would just become an x squared, assuming that x is greater than or equal to 0, you can't just say, oh, there's just an x, so no fractions, no square roots. You may have a square root in your work somewhere along the way, so you can't just look at the final answer. Look at here. Do you pick up any fractions, any square roots for f minus g? No, so once again, all real numbers. Any fractions or square roots along the way? No, all real numbers. So the first three, their domains are all real numbers, negative infinity to positive infinity. While I'm typing those in, you start thinking about f divided by g. What did we do when we had a fraction like this? How do we find the domain? Let me come back over here. And let's see here. I'll say left parenthesis, negative infinity, comma, infinity, right parenthesis. And I'm going to copy this thing right now. So for the next two, I can just copy and paste, and I can just paste them in. F minus g. And f times g. F divided by g is more involved. We're not going to produce imaginary numbers. This function is not going to produce imaginary numbers because there's no square root. But there is a time when we'll get an undefined result. When is a fraction undefined? When you have a number over 0. So you cannot allow 2x minus 7 to equal 0. So 2x cannot equal 7. So x cannot equal 7 halves. So if we were going to write this domain out in words, we'd say all real numbers except 7 halves. And very, very soon, I imagine they'll be doing that as the answers here in my lab get more AI graded. Then they'll probably have us writing it out. And I'll be grateful for that. I like that. But I'll write it out in words. All real numbers except 7 halves. That means it can be any number to the left of 7 halves. So negative infinity comma 7 halves. Notice it's a parenthesis, not a bracket. If you use a parenthesis of a bracket, you're including 7 halves. That's saying every number smaller than 7 halves, every number to the left of 7 halves. Or, how do we say all the numbers to the right of 7 halves on the number line? Oh, wait. Right there. Okay, what's in front? A parenthesis and then a 7 halves, comma, infinity. This is saying all the numbers to the left of 7 halves. This is all the numbers to the right of 7 halves. The only number that's being discarded here is the number 7 halves itself. I know interval notation is a way of disguising what you're finding, but that is the interval notation way of saying all real numbers except for 7 halves. Let's type that in. Left parentheses, negative infinity, comma, 7 halves. Get out of that denominator before you type your parenthesis. Union, left parenthesis, 7 halves. Get out of that denominator before you type that comma, and then you have a positive infinity, right. Addition, subtraction, multiplication, and division of functions is just plain old algebraic addition, subtraction, multiplication, and division. When you're finding the domains, though, you need to look through all your work and make sure no fractions, no square roots, all real numbers. The one that we did, f divided by g, it wound up with that fraction. You couldn't let the denominator be 0. Any questions there? Okay, number 2. An important quotient in calculus is the difference quotient. It's part of the definition of derivative if you've taken a calculus class. The difference quotient, it's a fraction, hence the word quotient. It's defined to be f evaluated at x plus h minus the original function all divided by h. And for the problems where they ask you to evaluate the difference quotient, they will tell you what it is. They'll say f of x plus h minus the original function all divided by h. You have to remember how function notation works. This first term here, f of x plus h, that's saying go to the function they've given you and replace every variable with x plus h. And that's the original function there. Looking at number 2, they give us a function. This is number 2. F of x is equal to the function x squared minus 1. They're breaking this into 3 parts for us. And that's how I'm going to find difference quotients. When you look at, here's number 2, notice they break it into 3 parts to make it easier to find that difference quotient. When you look at number 3, they're not breaking it into the 3 parts anymore. They're just saying, find the difference quotient. I'll still use those 3 parts when evaluating the difference quotient. So, first thing we'll do, let's find f of x plus h. This is part A. They want us to find f of x plus h. for f of x plus h. That says go to your function f, and wherever you see a variable, replace it with what's in the parentheses. So this may look sort of weird to you. We're going to come up here. We're going to replace that single letter x with x plus h. Oh, thank you. Thanks for reminding me to switch. There, thank you. We come over here. We've replaced that x with x plus h. We still have that little square on it, minus 1. This is a sum of two terms being squared. That popped up the first time this semester on the second day of class. We had something like let's see, what was it? A 2 plus 3i being squared. It wasn't just 2 squared plus 3i squared. What do you have to do if you're squaring a sum or difference? Now, remember this problem in right at the beginning of the semester? We'd write it twice and do what? We'd FOIL it out. That's how you find x plus h squared. Here's my scratch work. That's saying x plus h times x plus h. Here's my scratch work. I'm squaring x plus h. Write it twice. X times x is x squared plus, x times h. Here's what I'm going to do. If you have two different letters in the same term, write those letters in alphabetical order. X times h, I'm going to write it as hx plus, what's the inner product? Another hx. That's why I write them in alphabetical order, because now we can easily spot. Those are like terms. They can be combined. If you had this as an xh and that as an hx, you might not realize they could be combined. Plus last, h squared. So x plus h times x plus h. That reduces to x squared plus 1hx plus 1hx, that's 2hx's, plus our h squared. Here's the scratch work justifying that x plus h quantity squared is equal to x squared plus 2hx plus h squared. What else do I have stuck on there? Minus 1. Any questions on my logic there? This first part, f of x plus h, is usually the longest part of the problem. Suppose that had been an x cubed instead of just an x squared. Instead of writing x plus h twice, you would have had to do what? Write it 3 times. You'd FOIL that first 2, then you'd go through, distribute an x over every one of those, distribute another h over all of those, and combine like terms. I consider myself an optimist because no matter how bad the situation, I always think to myself, things could always be worse. Someone told me that made me a pessimist. I don't think so. Things could always be worse for y'all. You're not going to have any that have x cubed. You're not going to have to do the 3x plus h's, FOIL, and then combine like terms, distribute another x, distribute another h, combine like terms again. The biggest exponent you're going to have will be x squared. So you'll have to remember how we expand x plus h when it's being squared. Write it twice, FOIL it out. And there's my answer for part A. I may as well flip over and type it in before I get timed out. X squared plus 2hx plus h squared minus 1. Now part B. Here's something. You're going to use the answer in part A to answer part B. And you're going to use the answer you find in part B to answer part C in a moment. This is progressive. As we move from one answer to the next one, you use the previous answer each time. So if you understand what they're asking you to do with this part B, you're going to take what you just found, f of x plus h, minus f of x. That minus works like the old-fashioned minus. If you understand what they're asking for, you don't even have to show work here. This is saying, take the answer you found in part A. So we take what we found in part A, and this minus works like the old-fashioned minus when you were in elementary school. 7 minus 2. Your teacher would have said, 7 take away 2. That minus works like take away. So we have part A, take away the original terms. The f of x is the original terms. What's going to be subtracted off? You take what we found in part A, and you're going to take away the original terms. Well, x squared, there was an x squared in the original, so you've subtracted off the x squared. What else is going to be subtracted off? Negative 1 minus a negative 1. That's negative 1 plus 1. So that term's gone also. You drop off every term that appears in the original function. You're just left with 2hx plus h squared. And I didn't box in my answer for part A, did I? There's A. There's B. You take what you just found and take away the original terms. Here's something you may want to remember. In part B, the only terms remaining must contain the letter H. If you have terms that are left over that don't have an H after you do step B, you're doing something wrong. Every term will contain an H. So we come over here. Let's type in 2hx plus h squared Now we're ready to take the part we found in the answer we found in part B and divide it by this single letter H. This is part C. Going to take the answer you just found in part B and divide it by H. So this is the answer you found in part B. The answer we found in part B, that was a 2hx plus h squared. And you're dividing it by h. To simplify at this point, there's you have two approaches. You can factor out the common factor of h and cancel, or like we would do with those complex numbers, you can just split them up. I think I'll split up. I think that's quicker. Take the 2hx, put it over h, plus this plus right here is the plus I'm writing there. Then we take h squared and put it over h. We can reduce these fractions individually. We can cancel an h above and below on the first fraction. What are we left with? 2x plus, they can cancel an h above and below, and what are we left with? Just an h. For my final answer, 2x plus h. In a calculus class at this point, we would start asking ourselves, what happens to this expression as the value of h shrinks closer to 0? But we don't have to worry about that. All we need is the algebraic reduction. F of x plus h means plug in x plus h everywhere there's a variable, simplify. F of x plus h minus f of x. Take what you found in part A and remove the original terms. Everything you have should still have an h in it at this point. Everything you're left with there has an h, so every one of these, when you divide the terms by h, the h's will cancel out. And I'm going to be, for problem 3, I'm still going to go through these 3 steps here. And that is a 2x plus h. Number 3. I want us to find the difference quotient. We're not going to be typing in those other 2 answers, f of x plus h and f of x plus h minus f of x. All we're going to be typing in is that final answer. I think I'll go, let me write this problem down. Number 3. Seven x squared. Seven x squared plus 8x plus 8. And we want to find the difference quotient. Okay, the first thing we're going to do, we're going to find that f of x plus h. That says go to f, everywhere you see a variable, write in x plus h. So, everywhere you see that variable x, you're going to write in x plus h. And we need to simplify this. The order of operations says you deal with the exponentiation first, x plus h squared. Well, we just did that over here, x squared plus 2hx plus h squared, but I don't think it would hurt for us to do it again. Under ideal circumstances, by the time the final exam gets here, when you see x plus h squared, you remember x squared plus 2hx plus h squared. You don't even need to FOIL it out. Hopefully, you'll get to that point. But if not, hopefully you remember that says x plus h times x plus h. First, x squared plus outer hx. Y'all see why I write h times x is the same thing as x times h, but if we don't write them in the same order, you may not realize you can combine the two. You may not spot them as like terms. Inner, another plus hx plus h squared. You see, I told you it wouldn't hurt to do it again. X squared plus here 2hx plus h squared. You know something? We have something in front of all that stuff. What have we got in front of that stuff? A 7. We know what to do. We have a 7 sitting there in front. What are we going to do there? Distribute the 7. That'll give me, I'll get us started. That's going to be a 7x squared plus here 14, okay, 7 times 2 is 14hx plus, okay, 7h squared. What are we going to have to do here? Distribute the 8 to give us a plus 8x plus 8h. Do I have anything else? I still have that plus 8 stuck on there. And notice something. We combined our like terms right here when we were squaring the x plus h. You shouldn't have any more like terms to combine. Every one of the terms is a different term. Nothing you can combine. Any questions on f of x plus h? As I said, that's usually the longest part of the problem. Okay, now we're going to take away the original function. Take what we just found, f of x plus h, and take away the original function. I'll see people showing the work. They'll write that stuff down there minus, then they'll write the original function. If we're lucky, they distribute the minus sign, but in many cases they forget. And at that point, they messed up the problem. Everything else is wrong. The best way, the most successful way, is just to think about what they're asking you to do. This is part A. What we just finished. Take away the original. Which terms are going to be dropped off? I'll get us started. 7x squared minus 7x squared. What else? 8x minus 8x. What else? And the 8. That's right. The only terms remaining must have what letter? H. So sure enough, we have a 14hx plus a 7h squared plus an 8h. We took what we had, the original answer, and we took away the original terms. I guess I'll say we took f of x plus h's answer and we dropped off the original terms. The only thing left are the terms containing the letter h. We're now ready to perform that divided by h. Divide by h. Put each one of those terms over h. What's that giving me for a final answer? Here, 14x, I agree. 7h, I agree. So plus 7h and plus 8. For 14x plus 7h plus 8. $14x plus 7h plus 8. Any questions there? Okay, we've done operations, addition, subtraction, multiplication, and division. We've simplified difference quotients. Now the major part of this assignment. There's a new operation that applies only to functions. That operation is called composition of functions. We use little symbols for composition. We use little T's for addition, a little dash for subtraction, and so forth. They had to come up with a symbol to represent this new operation. Now, I think they came up with a pretty good one. Here we go. F composed with the G of X. Looks like it says fog. That's a little o. That's defined to equal f of g of x. And g composed with f of x. Suppose g, the function g had been written first. G composed with f of x, that means g is on the outside and your inner function is f of x. Composition of functions is really nothing more than repeated function notation. This is saying go to f, everywhere you see a variable, plug in g of x. This one is saying go to g, everywhere you see a variable, plug in f of x. We're going to do two things with composition. We're going to evaluate the composition at numbers, and then we're going to find the composition function in terms of x. Evaluating in terms of numbers, it's not bad at all, provided you remember how to use function notation. Let me write these two functions down. This is number 4. We have the function f of x is equal to the negative of x minus 1. The other function, oh, it's an h instead of a g. An h of x is equal to negative x plus 5. They ask us to find h composed with f of 6. We want to find h composed with f of 6. A composition at a number means your final answer is going to be a number. Those function, the h is written first, so that's going to be our outside function. Oh, thank you. Thanks. Oh, goodness. The h is written first, so that's going to be our outside function. On the inside, we have f of 6. Ignore that h for the time being. F of 6. We were doing this the last time. What is f of 6 saying to do? You're going to come up here to f, and wherever you see an x, you're going to replace it with a 6. So you have a negative 6 minus 1. Here's my scratch work. I've gone to f, I plugged in a 6. That gave me a negative 6 minus 1. What is f of 6 reducing to? I couldn't hear you. Negative 7, I agree. You still have that h on the outside. What is this notation saying to do? We're going to go to the function blank, and everywhere you see a variable, plug in blank. We're going to go to the function h, and everywhere you see a variable, you're going to plug in negative 7. So you have that little negative there. Replace the x with negative 7, and you still have that plus 5. What's that going to reduce to? What's this negative negative? The opposite of negative 7, that's going to become a positive 7 plus 5 gives me positive 12. There's my final answer. We plugged 6 into f. That gave us negative 7. We plugged negative 7 into h. That gave us a positive 12. It's repeated function notation. That's all it is, just repeated function notation. So we come over here to number 4, and that gives us 12. rather than going on to number 5 immediately, I have an example I actually wrote a note. I planned an example for y'all, okay? So I do have I have a page of class notes for today, okay? Now remember, we were generating ordered pairs, and at the beginning of that function notation section, didn't they have little things with ordered pairs, and we said, oh, is this a function and stuff? Here are 2 functions I have for us. The first one is f of x. F of x assigns 2 to 7, 3 to 5, 4 to 3, and 7 to 4. And we have another function. I'll name this one g of x. G assigns 2 to 4, 3 to 9, 4 to 5, and 7 is assigned to 3. And notice, these are definitely functions. Each x is only used one time for f. Each x is only used one time for g. So both of these things are functions. I want to find, here are the 3 compositions I'm looking for. I want to find g composed with f at 4, g composed with f at 7, and g composed with f at 2. Realize the first function that's written, that's the outside function. G is on the outside, and on the inside we have f of 4. First thing we need to do is find f of 4. Look at the function f. The function f assigns the x value. That number there is the x value for f. F of 4. What number is 4 assigned to when you use the f table? You're using the f table. No. 4 is the x value, so x is assigned to, 4 is assigned to 3. Okay. So now we need g of 3. You start off at the x value each time. You're starting at f. You go to 4 is assigned to 3. Now you go to g. What number does g assign 3 to? 9. 3 is assigned to 9 for my final answer of 9. F assigned 4 to 3. G assigned 3 to 9. Let's do g composed with f of 7. That means g is on the outside. What have we got on the inside? F of 7. Our starting x value is 7. F assigns 7 to, I heard 3 and 4. Which one? We go to F. Oh, I think, okay, be careful. You're going to F, not G. You go to F. 7 is assigned to 4. So we have G of 4. Now, what's G of 4? Use the G table. 4 is assigned to 5. The number that you're looking at to start off with on both tables, you're using the X row, and then it gets assigned to a Y value. Then use the X row assigned to another Y value. And one more. G is on the outside. What have we got on the inside? F of 2. Go to your F table. What number is 2 assigned to? 2 is assigned to 7. Now we go to our G table. What number is 7 assigned to? 7 is assigned to 3. Any questions there? Using the F table, 2 is assigned to 7, and then 7 is assigned to 3. If you understood this, you'll be able to tell me what number I'm going to type in for number 5 without me writing anything down. Okay, they give us 2 tables. They ask us to find fog 9, F composed with G. Okay, which table are we going to use first? The F table or the G table? Okay, I heard them both. So one of those answers is right. Which one will we use for that 9? Which table are we going to use? The G table. Using the G table, 9 is assigned to 7. Now we're ready for the F table. 7 is assigned to 10. You're starting on the inside, looking at the G table, 9 is assigned to 7, and then the F table, 7 is assigned to 10. Any questions there? Look at this one. They gave us some unnecessary information here. What's the big glaring piece of unnecessary information they gave us? G. We're not going to use G at all. It's just F composed with F at 6. So we start at 6. Using the F table, we're ignoring the G table because we're not using G here. 6 is assigned to 3. 3 is assigned to 7. Any questions on our logic there? And now we want to look at compositions at variables. Notice they're not giving us a number here. They want us just to find F composed with G, fog X, and G composed with F, goth X, fog and goth. So this isn't that bad. I'm hoping y'all are thinking this isn't that bad. For new stuff, it's not really that bad. Let me write the problems down though. This is number 7. We have f of x is equal to 9x minus 3, and g of x is equal to 6 minus 4x. Let me make sure. 9x minus 3, 6 minus 4x. And they want us to find fog x and goth x. We'll start off with f composed with g. Notice there's not a number to plug in. When you have a number there, your final answer is a number. When you have a letter there, your final answer is a function of that letter. So you should expect to see x's in your final answer. This says, take g of x and plug it into f. Take g of x and plug it into f. You're taking g of x and you're going to plug it into f. So we have 9. We're replacing x with 6 minus 4x. We still have that minus 3. g of x is the inside function. It's being plugged into the outside function. We take g of x, plug it in to f. And we can simplify this by doing what? Distributing the 9, we're going to get here 54 minus here 36x, and we still have minus 3. 54 minus 3, that's a 51 minus 36x. They'd also take negative 36x plus 51 as your answer. Doesn't matter which one you put in first. I think I'll put the constant first. Now they want us to go the opposite direction, g composed with f of x. And here's my advice to you. Rewrite the functions each time. I'm going to rewrite f of x. It's just easier to see what's happening if you start off with the functions, trying to use the same written there. Oh, you're taking this and plugging in over there. Too many ovals and arrows for my liking. Rewrite the function each time. Now you want g composed with f at x. That means this time you're taking f of x and plugging it into g. So we're taking f of x, this 9x minus 3, and we're going to plug it in over here for g. Y'all see what's happening? What's going to happen here? We'll have a 6, a minus, we have a 4, but we're replacing the x with 9x minus 3. Any questions? Can we do anything to reduce? Distribute? What are we going to distribute? Okay, don't subtract and distribute a 2. You distribute the negative 4. Good. So you have a 6 minus 36x. And what else do we have? A positive 12. Y'all are getting quiet. What's that going to give me for my final answer? 18 minus 36x. 18 minus 36x. Any questions there? We took f of x. This notation, I think it's 36 years. Well, let's see. If you count my 2 years at SFA and my year at Baylor, 39 years teaching experience says that when it comes to composition of functions, the fewer steps you show, the better. If you see what's happening, this is saying take g of x, plug it into f. You take g of x and plug it into f. This says the second function's f of x. So you're taking f of x, plugging it into g. Take f of x, plug it into g. For my final answer, I better type in the answer before I get timed out. 18 minus 36x. I need to point out something to you all. If you haven't already noticed it or figured it out, I better point it out to you. Let's see there. Operations are classified as commutative or not commutative. Addition The first operation you would have learned was addition, and that's commutative. A plus B will always equal B plus A. What about subtraction? A minus B, does A minus B always equal B minus A? Most of the times it doesn't. So I'll say not commutative. I have a little list of them here. Subtraction is not commutative. What about multiplication? Does A times B always equal B times A? Yes. So multiplication is commutative. Division. Does A divided by B always equal B divided by A? No, most of the times it doesn't. So now we have this new operation, this little fog and golf, that little O. Is that commutative? Does F composed with G always equal G composed with F? No, right here we see F composed with G started with 51. G composed with F started with 18. So if you get them mixed up on the test, you're probably going to have the wrong answer. Sometimes they're equal, but most of the times they are not equal. So composition is not commutative. So you make sure you know the difference between F composed with G and G composed with F. Fog, F composed with G, you're plugging G into F. Golf, G composed with F, you plug F of X into G. Any questions there? Let's find another composition. This is number 8. Well, I see a square root in this one, so it's really got to be bad. F of X is equal to 8X plus 3, and G of X is just the square root of X. Is my microphone working? It still doesn't sound like it's working to me. Okay. Y'all are sure. I need to be careful with that because I can't just stand up and let Tony take over today. So, okay. We want to find F composed with G of X. That's fog X. I'll draw the little arrows. That's saying take G of X and plug it into F. Take G of X. Oh, thanks. Oh, I keep forgetting. Oh, goodness. My brother's one indisputable contribution to this class is remembering to switch the screen for me. Okay. We take G of X and plug it into F. You take G of X and plug it into F. So we have 8. What are we going to write in place of that X there? The square root of X. And we still have a plus 3. Realize the plus 3 is not under that square root. And there's nothing else we can do. There's the composition, 8 square roots of X plus 3. So maybe just because there's a square root, maybe it isn't any harder. Maybe it's not necessarily harder just because we see a square root. Well, maybe it's more involved typing. You have to remember to use your square root hot button. Is this what I wanted to type? No, you've got to get out of that radical. Do a right arrow or click with your mouse or touch screen if you have one. My home laptop is touch screen. None of the things at the school are. I don't know if you've ever noticed there are times when Tony's here and I'm just here I'm sitting here writing and I'll see what he's doing. I reach over, I'm trying to tap on the screen and then I remember this is a touch screen. Okay. Now the opposite direction. G composed with F at X. Oh, wait a minute. I ain't gonna do that. Goodness. I'm gonna recopy the two functions. Sometimes the East Texan just comes back when I least expect it. There. You might be able to see, oh, I'm going to take this and plug it in over here. Oh, wait. Okay. Let me do it. There. You might be able to do all those arrows up there, but it just gets too messy for me. We want to find G composed with F. That says we're going to take blank and plug it into blank. We're going to take which function and plug it into which function. We're going to take f of x and plug it into g. So we're taking f of x, we're plugging it in over here to g. So we're going to have a square root, and that 8x plus 3 will go in place of that x. That means it's going to be all under the radical. For my final answer, there's nothing else we can do there. Any questions? So I have a square root, and then 8x plus 3 is all, and wait, where's the 8? 8x plus 3 is all under the radical. Any questions there? Back at what we did. Here we took g of x and plugged it into f. We took g of x, we plugged it into f. This notation was saying take f of x, plug it into g. So you took f of x and plugged into g. And notice something else. As I said, a composition at x, you get a function of x. You expect the variable x to be part of the be in part of your answer. Any questions? Number 9. We have f of x is equal, it's the same instructions, find fog x and goth x. Make sure, now on the test they may only ask for one part. So you need to make sure you know the order in which this composition works. F of x is equal to the square root of 6x, and g of x is equal to 1 over x. So f composed with g at x. Fog x. You take g of x and plug it into f. Do y'all follow those little circles? We're taking g of x and we're plugging it in over here in place of x. So we have a square root. That x is underneath the radical. That means, the 1 over x will also be under the radical. There's a little simplification we can do here. What's 6 times 1 over x? 6 over 1 times 1 over x. What's that going to give me? I couldn't hear you. 6 over x, I agree. For my final answer, Any questions on our logic there? 6 times 1 over x gave me the 6 over x. Let's go the opposite direction now. And notice since I'm trying to illustrate my thought process, you might not want to rewrite it each time, but it's certainly worth my effort. Reminds me of that colleague that time that said they couldn't write that quadratic formula down every time they used it in the homework. I said, well, I write it down every time. That helps the students remember. And we had the same conversation with a different teacher this past semester. So another teacher told me they couldn't write that quadratic formula down each time. Maybe they're like me with arthritis or something. I don't know. But I think it's neater if we rewrite the original functions each time. Here, this notation is saying take f of x and plug it in where? Into g. So you're taking f of x and you're plugging it in over here into g. Do y'all see what you have? You then have a 1 over, in place of this x, what are you going to write down? The square root of 6x. I remember at the beginning of the semester, we rationalized denominators to get rid of the denominator from the bottom. And you could do that if you wanted to. Multiply above and below by the square root of 6x over the square root of 6x to get the square root of 6x all divided by 6x. But I think this answer looks better. And this is where my lab, well, they'd take either one. I'm going to leave it like that. Let me punch in these answers. Oh, goodness. When I'm looking here and I'm writing, everything looks so neat. But then when I look here, I want to yell because it looks just like a mess, doesn't it? Well, let's see. What do we have? Looking at f composed with g, fog x, what am I going to click first? Look at that answer we had. Okay, so the first thing I'll do is I'll click that square root hot button. And then I have 6 over x. Now the second answer, what am I going to click first? I do that fraction bar first. And then on top, I had the 1 on the bottom. That's why I have the square root of 6x. Any questions? In most cases, f composed with g does not equal g composed with f. There are some rare cases where they do. Looking at number 9. They give us two functions. F of x is equal to 4x minus 2, and g of x is the fraction 1/4 times the binomial x plus 2. They ask us to find f composed with g of x and g composed with f of x. Same thing we've been doing. But they ask us something else here. Then determine whether f composed with g of x equals g composed with f of x. Under normal circumstances, what would that answer be? No, they normally don't. So, why are they asking us this? The mere fact that they're asking that makes me think maybe this is going to be one of those rare cases where they are equal. Let's see. Let me write down the problem. Number 10. F of x is equal to 4x minus 2, and g of x is the fraction 1/4 times the sum x plus 2. Well, I want us to find f composed with g, fog x. That says we're going to take the function blank and plug it into blank. We're going to take the function g and plug it into, we're going to take the function g, plug it into f. Take the function g, plug it in to f. So we have that 4 times, I'm making these parentheses extra big because we have parentheses there already. We're going to replace that x with 1/4 times x plus 2. Don't panic, this works out very nicely. We've replaced that x and f with g of x. Now, we need to simplify. This is multiplication. 4 times 1/4 times x plus 2. To multiply, you multiply from left to right. What's 4 times 1/4? What's about to happen there? I couldn't hear you. Oh. What's going to happen? 4 times 1/4. It's going to cancel out, isn't it? 4 cancels that 4 in the 4 outside cancels that denominator of 4. So the only thing we have left to multiply is just 1 times x plus 2. That's an x plus 2. Well, we still have what? A minus 2? X plus 2 minus 2. This works out really nicely. What's it going to reduce to? X. Everything except the x canceled out. So we come over here. F composed with g of x is equal to x. Now let's find it the other direction. G composed with f of x. Remember, I will rewrite f and g just because all that little circle and arrow stuff that I do gets a little messy. F of x is still 4x minus 2. G of x is still 1/4 times x plus 2. And we're finding g composed with f at x. That says take f of x and wherever you see a variable, plug it into g. So we're going to take f of x and plug it into g right there. So do y'all see what we have? We have a 1/4, and we have the parentheses. There's a plus 2 there. What am I about to write here? Which is 4x minus 2. Looking inside those parentheses, two things are about to disappear. What are they? The negative 2 plus 2. So all you have left is 1/4 times 4x. What's going to cancel out now? The 4's leaving us just 1x for the composition. Well, look at that. F composed with g of x reduced to x. G composed with f of x reduced to x. So they then ask, were they equal? And my suspicious nature saying maybe they would be because they were asking it. They don't ask it for number 8 or 9 or 7. But here, they were asking, in that suspicious nature of mine, maybe to think, yeah, they're going to be equal. And the fact that I've done problems like this for 20 years, and the program always has yes for these problems. So. Functions whose compositions reduce to x in both directions are said to be inverse functions. 1 week from today, if I'm remembering correctly, we have zeros of polynomials, and then on Wednesday, 1 week from today, we'll be looking at inverse functions, and I'm going to ask y'all, do y'all remember these problems here, number 10, where it was XX, yes, they're equal? Because that's the definition of inverse function. Two functions are inverses if fog x and golf x all reduce just to x. Everything canceled out except for x. And notice, as we were going through, look at the paperwork. How did the stuff cancel out? There we were multiplying by 4. Over here, dividing by 4. That's how the 4's canceled out. Here we had a minus 2. What was happening over here? It was a plus 2. Those opposite operations are being performed in order for everything to cancel out except for the variable x. And we'll see more of that the next time. Not the next time, next week. Number 11. Oh, and I think this is the last one. Number 12 is a cut point problem. So this is the last one. Well, this one looks sort of bad, doesn't it? This is number 11. Same instructions, though. Find f composed with g of x and g composed with f of x. Is f composed with g equal to g composed with f? Let me write this problem down. 9x plus 2. The cube root of 9x plus 2, and then g of x is equal to 1/9 x cubed minus 2/9. Same instructions as the previous problem. First one, we'll find f composed with the g at x. That says take g of x and plug it into f. So we're taking g of x and we're going to plug it in to f. So we have a cube root. We have a 9. We still have that plus 2 stuck on underneath. And what am I going to write here? The 1/9 x cubed minus 2/9. Looking under that cube root, there's one glaring operation we can perform. What can we do? Distribute that 9. So we have a cube root distributing that 9 times 1/9, what happens? So we just have 1x cubed. What about the 9 times the negative 2/9? The 9's cancel, just leaving you that minus 2, and you still have a plus 2 stuck on there. Something else is about to disappear now. That negative 2 plus 2. I'm beginning to think these functions are inverses. I'm beginning to think they're going to be inverses because all the stuff that's in the functions are canceling out. What's the cube root of x cubed? We see it in terms of the square root of x squared, but if the index is equal to the exponent, what do you cube? We're asking ourselves, what do you cube to give yourself x cubed? Just an x. That's right. That's asking you, what do you need to cube to get x cubed? Just a plain x. In general, if the index on the radical is equal to the exponent underneath there, you're left with just, this little green pen is so good. X. So, f composed with g of x, if I were running out of time, I would guess the next one's going to be x also. It's difficult to rig two functions such that the composition reduces to x in one direction and it doesn't reduce to x in the other direction. It can happen, but the problems have to be designed specifically for that to happen. Odds favor if one direction reduces to x. If they had this game in Vegas, I'd fly to Vegas, and every time they'd say, okay, the first one is X, what do you think the next one is? I'd say X. I'd bet X, and I'd walk away with more money than I arrived. Occasionally, they may not both be equal, but now we want the opposite direction, g composed with f of x. Oh, wait a minute, I got to recopy my function. I have a cube root of 9x plus 2, and g was, g is the 1/3 x cubed minus 2/9. 1/9, thank you. It would have canceled out then, I bet you. Okay, that's a 1/9 x cubed minus 2/9. This is saying take f of x and plug into g. So we're going to take f of x and we're going to plug it in over here for g. I'm going to write big. That means we have 1/9. Replace the x with that cube root of 9x plus 2. And that's going to be cubed minus 2/9. Something nice is about to happen. Something's about to disappear. Well, first of all, any questions on how we made the substitution? We took f of x, plugged it into g of x. So that single letter x became a cube root of 9x plus 2. Something nice is about to happen. What is it? The cube cancels out that cube root. So you have 1/9. The cube and the cube root cancel each other out. In a week's time, we'll be saying the cubing function and the cube root function are inverse functions. When they're performed consecutively, they cancel each other out, leaving us just 9x plus 2. And we still have that minus 2/9 stuck on there. Now what can we do? We can take that 1/9 and distribute. 1/9 times 9x gives us 1x, good, plus, what's 1/9 times 2? Be careful. That's like 1/9 times 2/1. What is that giving you? 2/9. And we still have, what's about to happen? They cancel out, leaving us x. So once again, these two functions are inverse functions. They perform the opposite operation in the opposite order. Here you're multiplying by 9. This one you're dividing by 9. There's a cube root. What undoes a cube root? Cubing. Here's addition. What have we got over here? Subtraction. And we'll see more of that in 1 week's time. And so XX, yes. Any questions there? Well, okay, I'm going to stop recording.